everyone. So this is basically how I'm going to be presenting notes each lesson. I will give you a video where I talk through the PowerPoint, and then you'll join me on Zoom to do any questions at the end. I know we'll have already talked this through on Zoom earlier today, but just in case you happen to have missed that Zoom. So that's going to be our general lesson structure. So if you can please title, date, mean drift velocity, it's not the 6th of December 2018 when you're seeing this. So whatever date it is when you're seeing this, please write that. And then throughout this video, if you can please pause and take the appropriate notes, that would be fabulous. So the first thing we're going to look at is something called number density. And the number density is effectively the number of free charge carriers in metals, that would be electrons, per unit volume. Now that per unit volume is really, really important. And when people do questions, they quite often forget about that final bit, that per unit volume. They just put the number of electrons because a question may give you that. You have to work it out by dividing your number of free electrons or free charge carriers by the volume to work out how much is, in fact, shall I write this? Shall we write this? Let's write this. Ooh, what am I doing? I'm going to go out in yellow. I'm going to make it smaller. So, a nice equation is number density equals number of, I'm going to put electrons, but know that it could be any charge carriers. Number of electrons divided by volume, which you can kind of tell from the definition, but I'm just putting it there for clarification. So you have a little look at the diagram at the bottom, and you will see that insulators on the left-hand side have a very low number density. They do not have many free charge carriers, and this is why they cannot conduct current. As you increase the number of charge carriers in a volume, so increasing the number density, you can see that materials get better and better at conducting. Some metals, I know we refer to metals being good conductors, they are. Some metals are better than others. So you can see there that copper has the highest number density, and so will have the best conduction. Semiconductors are in the middle there. You've got two there, silicon and germanium. I will go a little bit more into semiconductors. You do not need to copy that diagram, but if you make a note that basically insulators have a very few, low number density, few charge carriers, and conductors have a higher number, that should be enough to really summarise that. Okay, next bit, let's look at semiconductors. So semiconductors have a much lower number of density. And so to carry the same current as a metal, the electrons need to flow much faster. So effectively, if we want a metal and a semiconductor to have the same current, you need to have a higher speed of electrons. So previously in GCSE, we've talked about current being the rate at which electrons go past. Now that is affected by their speed, it's affected by the cross-sectional area of the material that you're looking at. So if you are able to fit 10 electrons past at a time, you're going to have a higher current than if you can only fit one, for example. So that's just a quick note there. If you can please make a note there, and you've also got that reminder of the equation, Q equals I times T. So current is how much charge passes a point per second. So going on to our next bit. Electrons moving. You can see we're all kind of linking here with the number density. Let me just move that out of the way. Slightly blocking. There we go. So electrons move in the direction of an electric field. However, they don't move in a smooth, straight line. Overall, they travel with a mean drift velocity, i.e. their net velocity ignoring all the random motion. Now you might be thinking, what on earth are you talking about? So I'm just going to basically draw you a diagram, and then I'll go back to the slide so you can make notes. Let's say you have a wire, and you attach a cell to the wire, making one end positive and the other end negative. So you've set up an electric field. The electrons, as I'm sure you know, will be attracted to the positive end of the wire because they are, of course, negative themselves and opposites attract. But instead of just travelling in a straight line like that, no, they instead basically zigzag all the way around. You can see it's getting closer to the positive end of the wire, but it is not a straight line. So overall, they are travelling in this direction, but that is not, it's not a straightforward thing. So what we say is that they travel with a mean drift velocity. So overall, how far have they travelled in what time? Ignoring the fact they're going upwards, downwards, sideways, backwards, etc. How far have they travelled in the general direction per unit time? So that's what mean drift velocity is. So again, if you pause the video, you make your notes, there is a little diagram on the right hand side there that does slightly summarise it better than my very messy diagram. So if you did want to draw that, you are more than welcome to. Okay, and the final, nearly final bit is current. Again, previously we've just very much talked about current being how fast the electrons are flowing. That's not really the case anymore. Here is an equation which links all, sorry, that looks a bit squashed off the side there. There you go. All the different factors that affect current. So, current is equal to A is a cross-sectional area. So again, I want you to imagine a wire that is this wide in comparison to a wire that is this wide. You will see that the one on the right-hand side with a larger cross-sectional area will obviously allow more electrons to flow through it, therefore having a higher current. So as I say, I is equal to A, cross-sectional area in meters squared, times number density, and remember that is per unit volume. That is very, very important. That's a T. That does not look like a T. Oh, I tried to make it better, it got worse. Anyway, times the charge on the electrons, because if you remember, it is charge per unit time, is our definition of current, times eventually the mean drift velocity, which, as we've already discussed, is the speed, and it's measured in meters per second. So again, if you can please take a note of that, you will be using it in a moment. Okay, we're nearly there. The effect of area. In order to maintain a steady current, when you have a bigger cross-sectional area, you have a lower drift velocity. When you have a smaller cross-sectional area, electrons have to travel faster to keep the same current, because obviously you have fewer electrons going through, so they've got to be travelling faster to maintain the same amount, eventually passing a point. So again, you can see a diagram on the right-hand side there, showing whether it's a larger cross-sectional area, you've got a lower drift velocity, and on the left, smaller cross-sectional area, higher drift velocity. And the important bit is that only happens if you are maintaining a constant rate of flow of charge, a constant current. Okay, quite enough talking from me. The last bit I'm going to get you to do is go to page 128 in the textbook. Georgia, just a quick note, obviously that is the single year textbook as opposed to the double year one, so you'll need to play that one by ear. And then I want you to take notes on the purple box, which is just about deriving an equation. It's very dull, but it's very useful for you to see where equations have come from. Then I would like you to join me on Zoom again, where we will go through the summary questions on page 130. So just to clarify, you should have taken notes from this section, done the deriving the equation from the textbook on page 128, and then you will join on Zoom and we will start doing the questions together. So it's not that you need to have done the questions by the time you get on Zoom, instead we shall do them together. All right, thanks everyone. See you later.